Good afternoon to everybody, and my greetings to all of you on the Earth Day. And after having a very stimulating talk by Sri Dr. Solanki, my talk would be a little dry in that sense. I'm extremely grateful to Dr. Kalai Salviji for giving me an opportunity to come here and give this talk on the Earth Day. And I thought I will talk about a project which is a very unique project and try to tell you about how it was done, what is its progress, and how this kind of a project can be replicated in the different labs. You all know about the earthquakes. I'm sure that many of you must have experienced also. In Delhi, on and off, there are always some shocks coming. And most of the time, the earthquake is happened in Afghanistan or in Himalaya or some other place, but you feel here. Those earthquakes are actually natural earthquakes. But also we are now seeing the earthquakes which are generated by our own activities. Dr. Solanki talked about the climate change, which our own activity is happening, but we also generate, our activities also cause earthquakes. Some of the examples are the reservoirs, the large-scale mining, petroleum exploration, hydrofracking, and many other such activities, which is a large engineering projects, also trigger the earthquake. Now, the difference between the natural and the anthropogenic earthquakes is, in normal earthquake, the elastic energy which is stored in the rock is released in form of a seismic waves, and that manifests in the ground motion, and then you can experience this. In the triggered earthquake, there is already a tectonic stress. The rocks are under some amount of a stress. Our activity works as a trigger to release that stress. And that is what is called as the triggered earthquakes. Now, one of the main reasons of such kind of an earthquakes is a creation of artificial reservoirs. And today, about 120 known cases where the reservoirs have induced a seismicity in the river region. One of the famous thing is the Hoover Dam on the Colorado in US. There are examples in Canada, China, Africa, and many other places. Actually, India is the leader. Dr. Harsh Gupta and his team in NGRI did very pioneer and original work on the reservoir seismicity. And this recognized world over that how this can be done. But all this work was done by taking measurement on the surface by using various instruments. And so we have not understood actual genesis of the reservoir triggered seismicity. This problem is world over. Nobody has an actual model that how it could be happen this. This is very important because if we can model this, we can do not construct such reservoirs in those places where such triggered earthquake can take place. So this is very important for all of us, not only in India, but the globe as such, that we need to understand. Now, which is the best site to study this? As I told you, there is 120 such sites where such things happen. Why others have not done it? The others have not been able to do it because of various reasons. One reason is that it is not possible for them to understand this because of the site characteristics. Many places, the initial after the earthquake, the seismicity died, or it is in the places such where you cannot go. But the Koina is one site where even after 55 years, the earthquakes are still occurring. So this is a very unique site. The second is, as you can see in this figure, you can see these are the earthquakes recorded up to 16, and you can see that when the reservoir level is up, the earthquakes are also higher. And when it starts unloading, also it happens. So it is very clear evidence that the loading of the reservoir and unloading of the reservoir do trigger earthquake. And this is going on for last several years. Now, so this site is still active. The other thing is the earthquakes are occurring at a reasonably shallow depth, about 4 to 7 to 10 kilometers. So when the idea is that whether we can drill a borehole, go there and measure what changes are happening before, after, and during the earthquake. So that is the main idea. Now, this kind of thing, why we call it the Lighthouse project? Because this will provide insight into reservoir-induced seismicity globally, and it will show that what should be done in future. So the Koina is in the first way, we found that it is a very ideal site, not only by the Indian scientists, but the globe over realized that this could be the extremely good site to study this. Now, such a large project, it has to be planned in a manner in which there is a consensus that how we should go about it. So we had a lot of consultation with the national, international experts. And then there is a international continental deep drilling project situated in Germany. We had an understanding with them. And we had a first international workshop. A lot of people from outside and India participated. It was a 5-day workshop to decide whether this is a good site or not. And then it was followed by also a national consultation. And we decided that before we take up actual work, we should have a clear understanding about the subsurface geology. So the first is the preliminary phase in which we tried that this is an area, and the yellows, circles which you are seeing, these are all earthquakes. Yellow are higher and the red are much higher. So this is a region where the earthquakes are occurring between two reservoirs, Koina and the Varna. So first we decided that we should have a 9 boreholes, which are not very deep, about a kilometer or 1.5 kilometer. And then this has to be instrumented. Also do a lot of geophysical survey, I will show you. Once you do that, you decide the pilot borehole based on what you get, which would be about 3 kilometer. This will be instrumented, and then you have an actual borehole. So it's a very long project. Its original plan was for about 20 years. Already about 7 years have gone out of that. So this is the area, and you can see this cross is where tentatively we had decided that this pilot boreholes will be there. Now, these are some of the detail. We don't get into the details of this, but you can realize the kind of intensity of the work which is required to be done as a preliminary site. One is the 9 boreholes. There would be geophysical logging in all this. Then there would be instrumented in the 6, where we will put seismometer to continuously record the seismic activity. Then there are certain studies about heat flow, magnetotelluric, all this to understand the different aspects of the subsurface geology and the geological mapping. So this is the first level preliminary study which was planned. The main idea was that whether we get some evidence of the fault, because with all seismic activity, there is a fault is associated. So these are some of the rock samples in the preliminary boreholes, which showed this is a granular flow, this is a silicon side, injected veins, the trachytes shattering. These are some of the evidence to show that the ground has moved below, and when something is moves, it will either shatter or it will get polished or it will create some fractures which will be later on filled by the water. So this all such evidences were we got. So we thought that yes, this is a right area and we have a reasonable good information. Also, this is some of the microscopic study. I'm not showing all the studies, but some few, which also confirm that this area is associated with faulting. And this is still active. It is the continuously happening, which we know with the seismometer, but the rocks also showed the same evidence. And some of the new information which came out, the first is we should know what should be the subsurface temperature. When you want to drill a borehole up to 3 kilometers, 7 kilometers, the temperature, what would be the temperature, whether we would be able to drill or not. Also, the temperature will decide the elasticity of the rocks. So we found that the temperature would be around 3 kilometers, it would be around 80, and around 130 to 50, around 6 kilometers. At the 1.5, which we had done already, it was about 56. So there is a method by which so we know that this temperature we can handle. There is no much of a problem. The first time the information came that the Deccan lava flows, those who are not familiar, but those who have gone to Bombay, Pune and all, you must have seen the hills which are will show a different structure. These are all individual lava flows. And this activity continued for 1 million years. And this information that how many lava flows were there was not available. Because whatever on the surface only we have mapped, the first time you got this information that there is a 46 different lava flows. Also, the rocks below are very old, about 22.5 billion years old. So you have a rocks which are 65 billion years. Immediately below, there are rocks which are 2.5 billion years old. So there is it means this area was outside sea. It never went into the sea for such a long time. And that is why you don't get much undulations. It is more or less flat because such a large time, if it is exposed to atmosphere, the various erosion, weathering and all, it will become a flat. So that also confirmed that there is it never went under. There is also indication that water did percolate up to these levels, about 1.5 kilometers. So that we got the information from the secondary mineralization, and then the cleavage or the fractures which were there, which were not the normal, it was in the other direction, so that it also said that it is due to this faulting. And the rocks, basement rocks were very weak. Unlike the normal rocks, these were very weak because of the seismic activities. And it is also, we also came to know that these rocks are not that strong, which can withstand a long stress. So even if the earthquake comes, it will not come very large earthquakes. So these are the preliminary information. There is actually a lot of other information, but this is the basic which we some of the new information came out. Now, based on this initial findings, we went to the government and got the project approved, where the all the details of the what we will be doing. The most important is to setting up a research laboratory, because this is a long-term project. You have to have a research laboratory which will do the drilling, borehole, core analysis, and other all research activities. And we will measure in situ properties of rocks, pressure, the pressure because of the water, whatever the fluid or gas composition there, what is temperature, stress, etc. And all should be measured before, during, and after the earthquake. That's more important. Once we do that, we will be able to understand how this faulting is taking place and what is the hazard of this area. And then, of course, model the reservoir triggered seismicity. So this is the main objective with which we started. And then again, there was a lot of consultation with the international community and the national community. And we decided that we will have a pilot borehole up to 3 kilometers and then deep borehole by the 7 kilometers. Now, it is also important that when the 67, when the earthquake took place, this is a fault which was no mapped by the Geological Survey of India. And our idea is that whether this fault is extending at depth below, because the earthquakes are occurring at the below. So we need to find out whether they are extending below or not. So this is an area which was chosen from here, that whether the fault extends. These are the surface expression, but we need to know whether they are extending below. And we also had evidence during that time that there was some helium data showed that this is the along this fault. So we concentrated on this fault. Now this is the pilot borehole design, where the initial, this is a Deccan trap and this is a basement rock, and we had to go into this basement rock. So a lot of analysis were done while drilling this. And what is most important we found is that between 2100 and 3000 depth is where the main fracture zone. So this is an area where the seismicity was confined. Now, one of the most important thing happened is about the drilling technology. This is the first time such a deep drilling in the hard rock was done in India. ONGC, of course, and Oil India, they do drill even deeper than this, but they are all in sedimentary terrains, not in such a hard rock terrain. So this, we had to do a lot of innovations in this, and there were experts we had from the ONGC and Oil India and our own. They decided to have a hybrid drilling, which is both to save time and cost. So don't worry about the technical, but initially it was a compressed air and then the drilling mud. There are different advantages, disadvantages of doing this, but basic idea is we wanted to drill fast, and this, of course, fast means it took about 6 months. And this region is in the area where you can't approach during monsoon. So you can do only about 6 months time you have for the drilling. And taking all such rigs and all itself was a major task. But it was quite complex to logistics of carrying out this project in a such inhabited area was itself is a major challenge. And then this is the some of the, during the drilling, this kind of cores are comes and immediately they are scanned and then labeled and then put it into this kind of a box. So it is all well preserved. So there are today we have about 13 kilometers of cores which is available for the research, and many people have been doing a lot of work on this. Now, what we found is that even this is a one example at about 1200 meters, and this is example around 2200. We found that the water is percolating right up to that. Now you can say, how do you say that this water is the same rainwater coming down? But there are isotope studies which can tell you that whether this is a rainwater or not. So this also has been done. And then what we found that the 7 zones, you can see that where the high fractured zones also coincides with the helium. And that is a crustal origin helium. So we can say that this is a fault and that this is matching pretty well. So the geophysical and geochemical data also match pretty well. So that means that these fractures are definitely of a seismic origin. Also, there are many others. When you do the drilling, you get a lot of other information, what we call as the breakouts, stress, and all you can see, this is a core between 200 and this area, which you see a lot of different fractures, which all again coincides with this kind of helium. So both the geophysical, geochemical data has been integrated, and we found that this definitely a area which is part of the Donaichiwadi fault, which is the main responsible for the earthquake, or it is subsidiaries. It's never a single line, it is a zone. So we have definitely went up to that. And then we also did a lot of stress. That means how from which region the fracture is happening. And most of the fractures are almost north-south kind of a thing. So this also showed that this is because of this fault only, these fractures have been developed, and they are allowing water to percolate below. These are the hydraulic fractures. So this also was proved to be correct. Then there are many other things which we wanted to know whether if so many earthquakes are happening in this region, whether we get any evidence of reactivation. So we get a lot of evidence of the reactivation, which is of the fault breccia, and this also the microfractures have been shifted. Also the EPMS studies also showed that there are a slick and slide against these microfractures. Isotope studies showed that the meteoric water, so that means this is a rainwater, and the strength of this rock is about 5 to 17 megapascal. That means this is a strength which is required for breaking of that rock. And that much pressure can be done by this water pressure in that. So all this showed that this is happening according to this. Also, there is a lot of other interactions which is we need to understand is how the chemically altered rocks, how this alteration is happening up to 3 kilometer depth, and that also a lot of mineralogical and microscopy XRD. We found a lot of clay minerals, which also showed that this water is allowing in going into the fractures and altering these rocks. Now, this is important because in the other areas also, the similar things were found. Now, the most important thing which came out of this study is that what is current assessment of the hazard. So what was found is that there are two reservoirs, the Koyna and Varna. What we found as the energy which is being released by these earthquakes is about 20% of the energy which is available at given time, while the energy which is generated by Varna is almost all is released. That means The this Koina seismic zone has sufficient energy already came, which can generate earthquake of a 5.8 magnitude if all energy is released in a single event. Now, that is important because this means this can happen in the distance of about 40-kilometer radius, and with earthquake occurs could be small, which normally the windows are shattered or the heavy furniture is moved. And when it is a 7 intensity, it can damage poorly designed or poorly built structures. So basically, it means that even if today earthquake occurs in 40-kilometer radius, there could be some kind of a damage. So we need to take care of that. All the structures should be built accordingly. So this is the one very important aspect came out from this study. Now, the second thing is we started with the limited data which is available to simulate whether this kind of a pore pressure can generate earthquake or not. So the different simulation was started with the different pore space at different permeability. Don't worry about all this, but basically it says that it will take about 5 years to generate enough pore pressure to cause an earthquake. And this Koina was built in 62 and the earthquake came in 67. So it says that pore pressure alone can generate an earthquake. Of course, this we have to further improve upon with the actual data which will come from the deep borehole. So basically what we understood that there is a definite water percolation down up to 3 kilometers. There are 7 zones. These fracture zones are associated with the fault which is responsible for the seismic activity, and the stress direction shows that this is active. There is a still activity going on. Oh, I'm going backwards. And the main important that the basement rocks, the strength, because of the recurrent seismic activity, they are fractured and there is not sufficient strength in that to produce a large earthquake. Of course, the temperature is 130 at this depth. So these are the main things which we will be using to decide the location of the main borehole. Now, the information which is generated, you can see that this is our pilot borehole and these are the seismic activity. This is the fault which is planned. Now, what we need to do is we need to reach to this place, which is around 7 kilometers or so, to find out what is happening exactly in the fault zone. So this pilot borehole will be now instrumented to decide the exact location. What happens is with the current, your location accuracy is about 500 meter or so, which is not good enough. You need to come about 50 meters. And to come to as near as to this, we will need a very close seismic data to find out. So, but you can see that we are very close to the main fracture zone, and now we will be planning to go to this region, either drilling the new borehole or extending this or whatever is feasible. So this is the proposed plan that we may go straight and then we can take a turn to reach to the borehole, because it is not possible to drill in the fault zone. And then there would be a variety of measurements which will be taken, and the about acoustic strain. These are all basically to understand the seismicity. Now, in this process, there are many labs are involved. Actually, my idea was that this is a kind of work which is not done by a single institute. There are several institutes are involved, both academic and research institute, including CSR NGRI is one of the prime which we have been uh, involved in this. So there is a lot of collaborative activity along with this. Apart from this main thing which we learned, there are many other studies have come. I mean, this such a large project, a lot of other things came. One is about the age of this basement rocks and whether they are continuation of the other old rocks, like what we call as a craton, which is the original basement rock. It generated about 2.5 to 3 billion years ago when the Earth itself was forming. So that is one. Also, the paleomagnetism, because there are magnetites and there are different reversals of magnetite, which is also in this, and this is also will come out. But the most important thing which came out is about the microbial diversity at that depth. The It was found at 3000 meter when the temperature is around 75 to 80 degrees. There is a viable microbial life. And this life in such a nutrient deficient and the high temperature, this is very important for us to understand because that will give us a clue that how the life originated during origin. Because this is the same type of rock about 3 million years old when the life started. So there is a strong connection between the rocks and the life. So this is a very good work which is being done at IIT Kharagpur by Dr. Pinaki. There's a lot of work on this. And second is also the rock, the bacterial activity in two different rock types is quite different. The type of genus you get in Deccan basalt, and these are quite different. I won't go into the details of that, but this is also tells us that how the rocks and the biology are connected. Now, the most important thing, this project is still undergoing, but still I wanted to tell you about this, is that we, in coming years, we should plan projects which we can lead, where we have the global leader position, like what we have in this project, and we can have the goals which are quite challenging, uh, not only from the science point of view, but also technology and logistics and the management, all aspects. Also, we need how to identify expertise and respect their identity and empower them. You have seen that more than 20 different institutes are involved. And so how to identify them, what kind of foreign collaboration would be required, what kind of a team. The most important is the multidisciplinary team. We have seen that you need different kinds of people, expertise in the geology, petrology, also structural geology, also in the different aspects of geophysics, biology, chemistry, and many others. So this is a very important to have, but all should have a shared vision. It cannot have, they have that different vision. And the most important is each member is authority is given to decide what it should be, but the responsibility still remains with the project director. So the execution of the project, responsibility of the project director, but each team member is authorized to take his own decisions. So this is a very new concept that how we can work in a team, in a large team with a multi-institutional team, where how to coordinate with each other. Now, as far as the leading such projects are concerned, the most important that we need to believe our own abilities. Most of the time we try to replicate what has been done, in the West, and then we said, okay, I have also done. But the important is now we should believe in ourselves that we can do something which others can follow. And that can come with the passion, commitment, hard work, self-discipline. The, that we should believe in ourselves that we are able to do this kind of a projects is most important. The second is how to communicate with your team when your team is multidisciplinary, multi-institutional. How best you can learn to communicate with them. That will come when you respect the knowledge of each team member and provide an identity to each of them. That means that part of the work he will get the credit, but his output will come into overall concept. Build mutual trust. This is again, I'm saying, delegate the authority, but not the responsibility. You can delegate the authority, but the responsibility always remains with the leader. And any adversity should be treated as an opportunity, which of course everybody does. So by doing this, when you do, you can build a very high performance organization, which has a very focused vision, consistent framing, policy and implementation. But the second is most important, that the culture, that the how you are able to convey your vision and values and the purpose to all the team members. And that culture will come only with the interaction. So without that culture, it is very difficult to have high performance organization. We should be able to build a passionate team so that they can find the problems and resolve them with innovative solutions. The next is the trust. The expectation at a different levels of the government, your governing board, or colleagues, collaborators, vendors, customers. There are various stakeholders in such kind of a large projects, and we should be able to build trust that these organization would be able to deliver. And the most important is encourage the criticism. When this project we were taking, I used to get barrage of criticism that it's impossible, nobody has done, so why you want to do, and all sorts of things. So I used to give them answer to each of that question. But the most important, I was telling them that I am doing because nobody else has done. And that comes because you have an ability in yourself. But you allow that criticism to come, so you can improve upon that. And the last but not the least, that we always worry about excelling, but we don't want to go to eminent position. I think more important for us is how to travel from excellence to eminence. We are normally very happy when our paper published in high impact journals and we say, I have excelled. I am in 1% of this, 2% of this, but that is not the eminence. You have to strive for the eminence. And I must thank Dr. Sukanta Roy, who is the project director of this lab, and his team for providing a lot of information. Dr. Harsh Gupta, who has originally seeded this idea, and many scientists of ISRO, MOES, CSR, NJRI, and many other research and academic, all have contributed to some way or other. With this, thank you very much for very patient hearing. Thank you.